Welcome to my channel Phi Concepts CHM. This is the second part of the series of band theory of solids. Here we are going to see about the Kronig Penney model. Kronig Penney model. In this diagram, the time-dependent Schrodinger equation for these two regions can be given as d square psi upon dx square plus 8 pi square m upon h square into E psi is equal to 0 for the region between 0 less than x less than a. Equation 1. For the second region, d square psi upon dx square plus 8 pi square m upon h square into E minus b0 into psi is equal to 0 for minus b less than x less than 0. Equation 2. By the Bloch theorem, the solution can be written as psi of x is equal to uk of x into e raised to ikx. Equation 3. Assume the total energy of the electron E is less than V0. We define two real quantities alpha and beta such that alpha square is equal to 8 pi square me upon h square, equation 4, and beta square is equal to 8 pi square m upon h square into V0 minus E, equation 5. Substituting in 1 and 2, equation 4 and 5, we substitute in equation 1 and 2. We get d square psi upon dx square plus alpha square psi is equal to 0 for first region and d square psi upon dx square minus beta square psi is equal to 0 for second region. This is equation number 6 and equation number 7. Solution will be of the form psi of x is equal to uk of x into e raised to ikx. We will take the first order derivative d psi by dx is equal to, using the UV product rule, we can keep e raised to ikx constant and differentiate uk of x. So that will be duk upon dx plus, now keeping uk of x constant, we differentiate e raised to ikx, that will be ik into e raised to ikx. Now take the second order derivative d square psi upon dx square is equal to, first we will deal with the first term, again apply the UV product rule. So by keeping e raised to ikx a constant, differentiating this term, it will be d square uk upon dx square. Now keep duk by dx a constant, we differentiate e raised to ikx, so that will be ik into e raised to ikx. Same thing we will do here. We will use the product rule by keeping e raised to ikx a constant, we differentiate uk, that will be duk upon dx. Then we keep uk constant and differentiate e raised to ikx. So the final term that we get is minus k square e raised to ikx into uk. Now we can add these two terms, they are the same. So we get minus k square e raised to ikx into uk plus 2 ik e raised to ikx into duk by dx plus e raised to ikx into d square uk upon dx. Substituting these in equation 6 and 7, this is equation 6 and 7, we have to substitute psi and d square psi upon dx square. We substitute here in this equation whatever we have got. And while substituting, in place of UK, we substitute U1 for region 1. Dividing this equation throughout by e raised to ikx, you get this. So all e raised to ikx terms will go. Then taking u1 common in these two terms, here we can write alpha square minus k square into u1. So this is a differential equation in u1. So this is equation 8, where uk of x is equal to u1 for the first region, 0 less than x less than a. Remember, we will be using this equation again to make some substitutions. This equation is for region 2, where we have replaced uk by u2. So you get d square u2 upon dx square plus 2ik du2 by dx minus beta square plus k square into u2 is equal to 0. Equation 9. This equation you can solve on your own and check. Where uk of x is equal to u2 for minus b less than x less than 0. The solution of differential equation 8 that we have got now is of the form u1 is equal to e raised to mx. So differentiating this equation, you get du1 upon dx is equal to m into e raised to mx. Again differentiating it, you get the second order derivative d square u1 upon dx square is equal to m square e raised to mx. Substituting all this in equation 8, we get m square e raised to mx plus 2ik m into e raised to mx plus alpha square minus k square into e raised to mx is equal to 0. Dividing this equation throughout by e raised to mx, we get m square plus 2ikm plus alpha square minus k square is equal to 0. Now we'll find the root of this equation using this formula which you are familiar with. So this is a quadratic equation in M. We find the root using this formula. We get M is equal to 2ik plus minus square root of minus 4k square minus 4 into 1 into alpha square minus k square upon 2 into 1. Opening up the brackets, these brackets, you get minus 4 square minus 4 alpha square plus 4k square. Both these will get cancelled out. So what remains inside the square root is 4 alpha square, and this is minus 4 alpha square, and that minus we have converted into I square. I square is minus 1. So this can be written as minus 2ik plus minus 2I alpha upon 2. 2 will get cancelled out and you get minus ik plus minus I alpha. That is m1 is equal to minus ik plus I alpha, that is equal to I into alpha minus k, and m2 is the second root, that is minus ik minus I alpha is equal to minus I into alpha plus k. Thus, the general solution is u1 is equal to a e raised to m1x plus b e raised to m2x. Substituting m1 and m2, you get u1 is equal to a e raised to I into alpha minus k into x plus b into e raised to minus I into alpha plus k into x. Equation 10. Where a and b are constants. Similarly, for equation 9, we can solve it and you will get m square plus 2ikm minus beta square plus k square is equal to 0. This is again a quadratic equation in m, and you can find the roots in this way and you get m is equal to minus ik plus minus beta. So you get two roots, beta minus ik and minus beta plus ik. So u2 can be written as ce raised to m1x plus de raised to m2x. So u2 is equal to ce raised to beta minus ik into x plus de raised to minus beta plus ik into x, equation 11, where c and d are constants. The values of a, b, c, d are obtained by applying the boundary conditions as follows. u1 of x at x is equal to 0 is equal to u2 of x at x is equal to 0. du1 of x upon dx at x is equal to 0 is equal to du2 of x upon dx at x is equal to 0. u1 of x at x is equal to a is equal to u2 of x at x is equal to minus b. du1 of x upon dx at x is equal to a is equal to du2 of x upon dx at x is equal to minus b. These equations represent equation 12. These boundary conditions are imposed because of the requirement of continuity of the wave function psi and d psi by dx at x is equal to 0. And hence u and du by dx at x is equal to 0. The remaining two conditions are required because of periodicity of uk of x. That is, u and du by dx are equal at a and minus b. On substituting and solving the determinant using equation 12. So equation 12, by solving that you get a determinant which will not be seen, the actual how it is solved. We get directly this equation beta square minus alpha square upon 2 alpha beta sin alpha a sin h beta b plus cos h beta b cos alpha a is equal to cos k into a plus b. Sin h and cos h are hyperbolic functions. This is equation 13. Under certain conditions, equation 13 is reduced, but the equation remains complicated. Kronig and Penney considered delta function v0 into b as finite. This is the delta function where v0 is tending to infinity. It is tending to infinity. The height is tending to infinity and the width b is tending to 0. It's very small. So v0 into b remains finite. Under such conditions, sin h beta b tends to beta b and cos h beta b tends to 1 when b is tending to 0. Therefore, equation 13 becomes beta square minus alpha square upon 2 alpha beta into beta b sin alpha a plus cos alpha a is equal to cos ka. Now we had seen equations 4 and 5 and where we had written alpha square and beta square. So we will take this difference of both as beta square minus alpha square. Substitute beta square and alpha square this way. 8 pi square m by h square is common and this is into v0 minus 2e. We have assumed that v0 is greater than e. So neglecting 2e, we get 8 pi square m v0 upon h square. So we can substitute this here. So substituting beta square minus alpha square here. This is 2 into 2. 2 into 4 is 8. Beta will get cancelled out. This 4 pi square upon h square we are writing as 2 pi upon h the whole square. Then we are multiplying and dividing this term by a, and here also a. And we are substituting in place of mv0ab by h cross square this as p. So this is p sin alpha a upon alpha a plus cos alpha a is equal to cos ka. Equation 14, that is the final equation. V0 into B is the barrier strength and P is the scattering power of the potential barrier. It is the measure of the strength with which the electrons in a crystal are binded towards a potential well. Cos K in the equation can take values between +1 and -1. Hence, the left hand side P sin alpha A upon alpha A plus cos alpha A will also have values between +1 and -1. So we will plot a graph of P sin alpha A upon alpha A plus cos alpha A, that is the LHS part, on the y-axis and alpha A on the x-axis. We get this kind of graph. P sin alpha A upon alpha A plus cos alpha A versus alpha A. We get this kind of curve. For each alpha A, we have plotted the LHS on the y-axis. So we get the value of cos Ka, from which K is determined. And from this you get these bands. The shaded parts are the allowed bands, and in between we get the forbidden bands. Thank you for watching my video.